In the realm of the nervous system, nothing is quite as it seems. In these brief moments, hundreds of events are taking place beneath the skin. The human body possesses millions and millions of specialized cells called receptors that look out onto the outside world. Many receptor cells are buried deep beneath the skin, and others are concentrated at the sense organs. There are light receptors in the eye, sound receptors in the ear, touch receptors in the skin. These receptor cells are highly sensitive to changes in energy, such as light and sound, and respond by producing tiny electrical impulses which alert the brain. Receptor cells in our sense organs are the information gatherers of the nervous system. Each of these receptors detects energy of some kind, such as heat, light, and sound. When activated, the receptors respond by translating the stimulus into an electrical signal, a form of energy which the brain can understand. This is the nerve impulse. Energy exists in many forms. Through this thermal imaging camera, we can literally see the transfer of heat energy. When a hot cup of coffee spills out onto bare skin, heat energy sets off a chain of events which causes Emma to react. As heat energy pours onto Emma's skin, the pain receptors attached to nerve endings respond to the dramatic change in temperature. Here we see the nerve impulse as it travels along the length of the neuron. The nerve impulse travels through Emma's body at a velocity of up to 120 meters per second. Soon she will feel the heat. But the speed of Emma's reactions will depend on the route the impulse takes through the nervous system. The nerve impulse travels along a sensory neuron. It then loops back to begin the second part of its journey along a motor neuron to the muscles in Emma's arm. When it arrives at the muscles, just microseconds later, they contract. This reaction is automatic. It's a reflex action, a simple survival mechanism for those occasions when our brain would take too long to respond. This reaction has taken place so quickly that Emma hasn't yet realized what's happened. It'll be another fraction of a second before she cries out in pain. But what causes this delay between the reflex reaction and the cry? The answer lies in the way in which the nervous system is wired. The heat on Emma's skin triggered an impulse from the receptors along the sensory neuron to relay neurons in the spinal cord, eventually reaching the pain centers of her brain. Emma finally realizes what's happened, and her response is to cry out. What's happened is that nerve impulses sent along sensory neurons have finally reached the brain. The brain responds by emitting nerve impulses of its own. This is called coordination. In these short moments in the life of the nervous system, Emma has had to process and respond to hundreds of sensations. At the end of the day, she hears, feels, smells, and sees her brain's interpretation of the world.
We're in Port Jefferson, Long Island. We're about 55 miles, 60 miles from New York City. And this is where I do a lot of my training since I've been involved in the Paralympics the past 10 years.
In the case of athlete Todd Schaffhauser, the story of the nervous system takes a strange twist.
I lost my leg 11 years ago to cancer, and I was on chemotherapy for a year and a half after that time. After my chemo was over, I was inspired to get involved in sports. So I got involved in the Paralympic Games. And it took 2 years to qualify, and I made it to Seoul, Korea, and then I made it to Barcelona, Spain.
Todd Schaffhauser is a serious athlete who's shown remarkable courage in the face of disability. It's his dedication to sport which helps him overcome a curious condition that contradicts what we know about the nervous system. The condition is called phantom pain.
The first time I experienced phantom pain was right after I had the surgery in the hospital. I woke up in bed and I felt like my leg was very itchy, and not knowingly I went down to scratch it, and then I realized my leg isn't there anymore. So it was something which was just a real weird experience. I thought I was crazy.
Todd Schaffhauser is far from crazy. The pain he suffers from is not psychological, it's physical. Yet his phantom pain is odd. Without receptors or neurons, there are still periodic sensations from the missing limb. To try and understand his condition, we first need to have a clear insight into what's happening in Todd's good leg. Each time Todd's good foot hits the ground, hundreds of nerve impulses are generated and travel to Todd's brain along a network of neurons. It's a long journey of over 1.5 meters from head to toe. To travel this vast distance, a chain of interconnected neurons are needed. At the point where one neuron meets another, there's a tiny gap called a synapse. When an electrical nerve impulse arrives at the end of a neuron, it cannot travel any further. Instead, the impulse triggers the release of a special chemical called a neurotransmitter. It's this chemical which bridges the gap between the two neurons. As it crosses the gap, the neurotransmitter diffuses into the next neuron and kick-starts the formation of a new nerve impulse, which continues the long journey to the brain. Following Todd's amputation, there are clearly no neurons between his missing limb and his brain, and yet he still feels sensations from a limb that isn't there.
7. Last one. That's good. Come back. Okay. Now those 4 exercises, what you do is you start out each with a set of 8. You need to reset.
These phantom sensations aren't unique to Todd. He now runs exercise programs to help alleviate an all-too-common experience for amputees.
Up and back.
My first bout with phantom pain came about a week after my amputation. I was sitting in my room in my wheelchair, and all of a sudden it felt like my left leg was back, and somebody had a vice, and they were cranking this vice down on my ankle.
I haven't had it that much. Right now I'm sitting here wiggling my toes, and I know they're not there, but they feel like they're there.
There's times when you go to take medication, and I'm the type that says, what am I taking the medicine for? A leg that's not there. And I also have been asked, how did I adapt to losing my leg? I said, I adapt to losing my leg very well, but I have not adapted to phantom pain. Fine, but it's so real that it's unreal.
Mm-hmm. I had a dream.
When amputees say they feel pain from a limb that isn't there, we would be wrong to say they're simply imagining the pain. For Todd and his fellow amputees, this discomfort is as real as any other sensation. Now, scientists believe they can explain phantom pain. The answer lies in the brain. Within the brain, are regions which deal with sensations from different parts of the body. Called the sensory cortex, this is the part of the brain that deals with Todd's legs. The part of the sensory cortex devoted to receiving messages from Todd's missing leg is still active. Shown here, marked yellow, scientists believe that this area is being colonized by its neighboring cells. It's receiving sensations from other parts of the body. In simple terms, Todd's nervous system has become cross-wired. In another area of disability, it's the very adaptability of the nervous system that enables students like Sally Clay to achieve their full potential.
It was a bright, cold day in April, and the clocks were striking 13.
The physical act of reading Braille is not easy, but people like Sally are able to do so because the touch receptors concentrated in the tips of her fingers make it one of the most sensitive areas of the body.
Enough to prevent a swirl of gritty dust from entering along with him. I learnt it in about 1993, and I was taught it by a sort of peripatetic teacher of Braille that came twice a week. Voyez-vous? Voilà. Une raison tout à fait convaincante. I'm doing French, German and music. And the Braille for that is quite bulky in some respects. Like Braille music's very difficult to learn. French and German Braille aren't that hard.
Élise maintenant.
Où saigne en scène?
Oui.
Point.
Wow, jamais. Alphago?
In some ways, our sense of touch and our sense of sight are very similar. Both touch and sight use special receptors and transform stimuli into messages that the brain can understand.
Oui.
Instead of going in through your eyes, and you say, you know, that's an A, that's B, you don't think like that. It just goes in through your hands, and I can picture it in front of me, what's on the page in my head.
Je veux que vous vous mariez, s'il vous plaît. C'est là, ma fille.
Okay. This is a Brailler, which basically is a way of writing Braille. It's a Braille typewriter, which is a when you use this, you can punch out the 6 dots in different combinations. So if I type an A, which is just 1 dot on its own, the top dot will come out. So
Braille is made up of 6 dots which make up a cell. The precise combination of these dots in each cell forms the alphabet of Braille.
There's different reading fingers, okay. So the first letter there is, the first, like, probably what feels like a clump of dots to you is S.
So how am I supposed to tell?
The touch receptors in the fingertips can detect pinpricks 1.3 millimeters apart. To read Braille, the fingertip sensitivity is pushed to its limits.
Right,
Yeah.
I can feel... Hang on. It's difficult.
Sally's sensitivity has come from years of reading Braille. It's due to this constant practice that the part of her nervous system devoted to touch has become far more sensitive than a sighted person's.
You can feel and distinguish the shapes of the words.
Okay, I can feel 3 dots there. I can feel it with my nail, but I can't actually tell.
Yeah, are you actually moving your finger along?
Yeah. And then I get completely lost. If I move my hand around, I get lost.
When Sally touches the raised dots, the friction between her finger and the paper stimulates the touch receptors in her hand. As with all receptors, triggering nerve impulses in Sally's fingers depends on something called the all or none effect. This is where the receptors in Sally's fingers are sufficiently stimulated to cause a nerve impulse. With a row of dominoes, the strength of the first push or stimulus has to be above a certain threshold or the dominoes won't fall. In the same way, the stimulus within the nervous system has to be a certain strength to start a nerve impulse. This is why it's called the all or none effect. There are only two possible outcomes. Either a nerve impulse is triggered or it isn't. For a sighted person, the fingertips are less sensitive and require greater stimulation. If the threshold potential isn't reached, the dominoes won't fall.
On then. No, not my prawns.
I'm looking.
Get off my prawns.
In the nervous system, there's very little difference between touch and sight. A sighted person recognizes a chess piece because light energy strikes the light-sensitive receptors in the eye. For a non-sighted person, it's the touch receptors which receive the vital stimulus. But in both cases, an electrical signal carries a message through the neurons to the brain. The order is always the same: stimulus, receptor, neurons, central nervous system, and the brain. Neurons form the pathway between the senses and the brain. As we grow and learn, they're constantly forming new connections. Here we can see the process taking place. As nerve cells grow, they seek out and form synapses with other nerve cells. It's a process that never stops. In the brain, these connections reach their most complex. The brain is a dense mass of billions of neurons. The complexity lies in the connections, and it's here, in this web of interconnecting neurons, that our higher functions exist. It's here where we form our ability to think.